Hey, just a reminder that the 9th problem set, the second to last, is due on Friday. I delayed it because I didn't put it up early. The last problem set will be after Thanksgiving. Okay, what I wanted to do before starting to talk about automobiles is revisit the real air conditioner, just walk you through it carefully so that it makes sense. Partly because it's a device that you encounter all the time, either as an air conditioner or as a refrigerator or as a dehumidifier. And partly because there's still a fair amount of physics in it that you might as well understand, and you've got the pieces to understand it. So the basic big picture idea is that it's moving heat from a colder spot to a hotter spot, an action that doesn't happen naturally in nature. Heat doesn't naturally flow from hot to cold. It's got to be pumped. So the air conditioner is a heat pump, and it uses the classic air conditioner uses a special closed cycle movement of what's called a working fluid, so a chemical that ultimately carries the heat. It sends that working fluid through a cycle, and that cycle moves heat from the cold side to the hot side at the expense of electric power. It consumes. It needs the order that's present in that electric power to do the pumping. So in principle, you can use things other than electricity to do it. And actually, historically, there were air conditioners that operated on natural gas. That's another long story, but it's possible to do that. So these are all of our current ones, normal ones around the house, operate on electricity. So I'll put up a slide. I won't dim the lights. I'll just put the slide up so you can see my picture of the closed cycle. The idea is that the working fluid moves its way around this loop, always clockwise from your perspective. And it goes from outside, which is on the right. Where's old school pointer? This is outside, this is inside. I made this blue to make it cold, to illustrate that it's cold. I made the outside hot because it's a summer day. And this fluid is going to go around that loop over and over. And I'm referring to it as a fluid because it goes back and forth between being a liquid and a gas. And it does that for reasons that we should understand based on the experience with water, steam, and ice. So around that fluid goes, it's going to pick up heat inside, carry it with it, and then release it in the outside. And in order not to violate the law of entropy, it has to consume order to make this happen. And the order is coming from electricity, and so electric energy is going in, and it's becoming thermal energy. It's losing its order. And that thermal energy ends up in the great outdoors. So that's the illustration. Here's the reality. And let me walk you through it. So I won't turn it on, it just buzzes away. The loop is closed, as I said. The working fluid never leaves. In principle, it stays in there certainly for the working life of the device. If it leaks, you lose it stops functioning properly. And so when people come to service your air conditioning unit at home, or it might be called, instead of an air conditioning unit, it's called a heat pump, they are often checking on the amount of working fluid that's present. Have there been any leaks? Is it all there? Okay. One potential failure of all these heat-moving devices is the loss of the working fluid. So let me start somewhere, and I'll do it like I did last time, but too briefly. Let me start with the fluid traveling through this very thin pipe up here, if you can see it. Actually, I probably can. No, I can't do three things at once. Okay, I'll follow it moving through this thin pipe. This thin pipe corresponds to the bottom of that drawing, where the orange arrow is pointing to the left. There's a liquid working fluid traveling through this pipe at sort of normal temperatures. Whatever normal, the temperature, it's colder inside than outside, but we can let's say normal sort of in between. So it's at sort of normal temperatures. It goes through a valve, that constriction that's up there on the drawing, which is just a device that uses things familiar to us, viscosity and so on in the liquid, to allow the liquid to go from high pressure liquid to suddenly low pressure liquid. The liquid enters a chamber, a big cavity from its perspective, where the pressure is low. That's this entire shiny coil here. This shiny coil is called the condenser, or alternatively the evaporator. Up there it's written as the evaporator. No, it's not condenser. It's never condenser. It's always evaporator, sorry. It goes into this evaporator. Read my own writing, it's good. The evaporator. The liquid, having entered this region where there's very little pressure, suddenly discovers that assuming that there is even a tiny pocket of gas, that the landing-leaving process is out of balance. Because if there's a tiny pocket of gas at low pressure, it's low density. And so molecules in that gas rarely land on the liquid surface. So molecules leave the liquid surface rapidly, but they don't return to the surface fast enough. So there's a phase transformation. The liquid evaporates to become gas in this low pressure environment, just as water on a table evaporates to become gas in very dry air, in air that has almost no water molecules around it. Okay? So it evaporates, and that evaporation takes energy. The molecules that were clinging to one another as liquid now are sent off on their own. That energy comes as thermal energy. The evaporator begins to soak up thermal energy from its environment, including your room air. So this is, if your room air is dry, you can do the same process by simply evaporating water in your room. And they do this in dry area, desert areas. They do it. You just put out water and it evaporates and it cools the room. In this case, it's happening inside a container, and it evaporates and it cools the room. And of course, the molecules don't leave the container. They're trapped, ideally forever. And they wander out of this pipe and into a compressor. So they've soaked up a lot of thermal energy from the room by virtue of becoming very cold. Having used the thermal energy to evaporate, it becomes very cold. It cools the room air that goes across it. This is a heat exchanger, meaning that it transfers heat from inside to outside or outside to inside, but it doesn't transfer molecules. That's what a heat exchanger does, is it moves thermal energy without moving stuff. Radiators are heat exchangers. So the gas comes out of this having absorbed lots of thermal energy. It goes into a compressor. And the compressor's job is, as the name suggests, to pack the molecules more tightly together. An action that takes work, because you have to push them inward as they move inward. So the compressor does work on the gas, taking it from low pressure, low density before to high pressure, high density after. Okay? That's the top horizontal line up there on my drawing. And it's traveling through this pipe here as it comes out of the compressor. The compressor is this big black pot there. Incidentally, one of the main, apart from leaking its working fluid, the classic failure of any of these heat pumping systems is the compressor goes bad. And alas, it's the most expensive part in the whole system. So those of you who have families that have had to replace essentially their air conditioner or heat pump, it's usually because the compressor fails. So it compresses the gas, and this now at the far end is high pressure, very hot gas. It's high pressure because we pack the molecules tightly together. It's high temperature because we've done a lot of work on it. So what comes out here to enter what's now called the condenser, and now I'm naming it correctly. The condenser, the right side of that drawing, is hot, dense, high pressure gas. And now if there's even a tiny drop of liquid around, the landing-leaving process is out of balance again. The molecules in that dense gas land so often on the liquid that the liquid's the molecules leaving the liquid can't make up for it. So basically, the gaseous working fluid condenses into a liquid in this environment because the high density. This is the same as what happens when you send steam out of a teapot into a cold environment. It just condenses into droplets. The landing-leaving process, again, is out of balance in that case. The dense steam molecules, they're landing much faster on the surface than they can leave. So you get a net accumulation of liquid water in the steam story. You get a net accumulation of liquid working fluid in this story. Okay? So we evaporated the working fluid from liquid to gas in the evaporator. We condensed it from gas to liquid in the condenser. And having it turn it back into a liquid, it goes back through the little thin tube to start the cycle over again. And it does it all day, over and over, round and round it goes. Okay? And the work that is done by the condenser in compressing the low-density gas to high-density gas never reappears as work. Where does it go? It comes out as thermal energy in the hot side. So the air conditioner delivers to the hot side all of the heat that it absorbed from inside, plus all the electric energy it took from the power company and turned into thermal energy. Is that okay? Before I leave this then, is anything coming in here? Oh, no. About the heat pump. What if you use the heat pump? Because here, particularly in Virginia, people use heat pumps not only to cool their houses during the summer, they use those heat pumps to heat the house during the winter. How's that? In the winter, you flip some valves in the heat pump. The compressor's still doing its trick. There's still an evaporator. There's still a condenser. But their locations are reversed. In the winter, when you're trying to heat your house with a heat pump, the heat pump absorbs heat outside. It makes a cold evaporator outside, soaks up heat, carries it as a gas, as the low pressure gas, into the house where it's turned back into a liquid and condenses. The exact location of the parts I got to be a little careful about. But basically, it's running backwards. It's soaking up heat outside, which is cold, and dumping the heat off inside, which is hot. It's moving heat against its natural flow again, but now it's carrying heat into the house. And this all works just fine. Again, there is so much thermal energy around in the world, you can go find it even on cold days. It's out there. So if you feel the air coming off the outdoor unit of a heat pump right now, it will be colder than the air around it. It's actually refrigerating the cold air even farther, carrying the heat inside and dumping it off. And like, why would you do this? Why wouldn't you just use the electricity and turn it right into thermal energy? And that's what you can do with a space heater. Space heater, in my mind, is just sort of a generic term for a device that takes electricity, or since it's coming steadily, it's taking electric power coming in, 1,000 watts, and turning it directly into thermal energy, 1,000 watts. And over the years, I've collected, didn't bring up, a whole bunch of advertisements for various fancy, decorative space heaters. They're all the same. They're all 100% efficient, which they will tout as some revolution. It's not. If you buy 100 watts of electric power and you just crush that electric power into thermal power, destroy its order, you can get 100 watts out for every 100 watts of electric power you bring in. Is that okay? Electric light bulbs do this. Sort of almost everything does this, but it usually does something interesting on the way. I don't know what this computer here probably uses, let's say it uses 50 watts to do whatever it's doing. At the end of the day, it's a 50-watt space heater, because almost all the action, when the dust settles, the electric power, 50 watts of it, has been crushed and destroyed into thermal power. You guys are 100-watt space heaters in effect too. Okay, that's another, but that's not not electric. Okay, so you can use space heaters, which just take electricity and turn it into thermal energy, and they're 100% efficient, which sounds great. You buy 1,000 watts of electric power coming into the house, you turn it into 1,000 watts of thermal power, it makes things warm. It may make things warm in local places that you like, and that's good, but basically, the best it can do is 100% efficiency, which sounds like the best possible. It's not. You can do better than 100%. And the way you do better than 100% is with a heat pump. So to put numbers on it, approximate numbers and talk the story through, suppose it takes 5,000 watts of thermal power to keep your house warm and nice. This is determined in part by how quickly heat flows out of your house into the great outdoors. So let's say you need 5,000 watts right now to keep it steady at a comfortable temperature, the temperature you like. You could buy 5,000 watts from an electric power company and send it through space heaters and get your 5,000 watts of thermal power, and everything will be great. But you can do better, and the way you do better is you buy 1,000 watts, just maybe a fifth the power, to run your heat pump. And what the heat pump does is it goes outside and it gathers 4,000 watts of thermal power from the surrounding air and carries it inside at the expense of 1,000 watts of electric power. And what is then dumped off inside is both. It's the 4,000 watts you gathered of thermal power plus the 1,000 watts that you had to create out of electric power. So 5,000 watts shows up in the house, but all you bought from the electric company is a fifth of that. So that's what heat pumps do for you. Is if you're willing to work with electric heating, and the alternative is gas heating, or fuel oil and stuff, that's a whole other different story. But if you've got electricity to do your heating anyway, don't just turn it into thermal power. Use it strategically to move heat inside. That works fine. I mean, in principle, it's always a good thing to do. In practice, the bigger the temperature difference across which you're trying to move the heat, meaning the colder it is outside and the hotter you want to make it inside, the bigger that temperature difference, the more order you have to consume to move every joule of thermal energy. So if it's bitter cold outside and you want to make it toasty for tropical plants inside, you may end up using so much electric power to make the move that you're not doing a whole lot better than using a space heater. If you factor in the fact that the heat pumps, first of all, they cost a lot of money and they've got a finite lifetime. And second off, they're not 100% perfect. They don't achieve the theoretical ideal of how much heat they can bring in for a certain amount of electric power consumed. So when the dust settles in colder climates than Charlottesville and in Virginia, it gets a little iffy on using heat pumps. You may just do better with just a space heater. But in Virginia, which doesn't get super duper cold, you almost always can beat a space heater by using a heat pump instead. Okay? Questions about that idea? Why doesn't the fluid lose its heat again once it starts to move to warm and just release it back into the cold? The fluid is going through a cycle where it's being forced to condense in one location and the act of condensing it makes it release its latent heat of evaporation. A huge amount of heat comes out of it as it condenses. And that is sent out into the room and is lost to the fluid. The fluid now has less energy than it had before. The fluid then travels inside as a liquid, and then it evaporates. And in doing so, it needs a latent heat of evaporation, which it soaks up from its environment. And that heat now is in the fluid. The energy of the fluid actually went up. And so you set it back outside, you go through the compressor, add still more energy, and then make it cycle through. So because different activities are happening inside and outside, it's a one-way transfer of heat. You're transferring heat from the cold one to the hot one deliberately. I hope that answers the question. Other questions? All right. So that's the world of air conditioners. I'll remind you that their efficiency gets better as the temperature difference across which you're pumping gets smaller. It's easy to chill something by 10 degrees from hot to cold, from cold to hot. It's harder to do at 100 degrees. And that's for theoretical reasons that have to do with the amount of entropy that's being undone by moving heat from very cold to very hot. You're getting rid of a lot of entropy in doing that. You have to pay big time to do that. You have to make up that entropy. Okay, where I want to go next is automobiles, and particularly, automobiles as a moving target. At this point, there still are internal combustion engine automobiles. That may not be true 20 years from now, but internal combustion engine automobiles provide mechanical power, and they get it from thermal power. So they're somehow turning thermal energy into mechanical work energy. That's, it seems like an impossible, no-no. And with that in mind, let me ask you a question here. Where is it? There it is. A car burns gasoline to obtain energy, really, to obtain work, but allows some heat to escape into the air. You certainly have noticed this with cars, that it's often very hot around cars. Could a perfect gasoline-burning car avoid releasing any heat? You okay with the question? See what you think. We'll do it to 30 seconds and I'll call it. 4, 3, 2, 1, 0. No is correct. You can't do it. The reason you can't do it is because once you burn the gasoline, and its energy now is in the form of thermal energy, you have again crushed the energy into dust, and it's now thermal energy. You can't turn that thermal energy entirely back into work. If you did, you would get rid of the entropy that was in that thermal energy with nothing else happening. And you can't get rid of entropy. You can't make it go down. On the size, on the scale, the largest scale, entropy is always going up. In principle, it can stay exactly constant, but it never, you never get that. So the point of asking that question is to point out what is happening in a car. It is not taking the thermal energy in the burned gas and just turning it all into work. It can't. That's forbidden by the law of entropy. Instead, it's taking advantage of the fact that you've got this hot burned gas and you've got this cold outside. That's two objects that are at different temperatures. So if you let heat flow the way it wants to flow, from hot to cold, that by itself will make entropy go up a lot. That's the way heat loves to flow. Because entropy is going up naturally as you let the heat flow, you can sidetrack some of that energy. You can pull it aside mechanically and with sophisticated processes and turn it into work. And the bigger the temperature difference between the hot and the cold, the more order there is present. And therefore, the more of that energy you can sidetrack and turn into work. So I told you that there exist lots of these are called heat engines. I mean, just generically, the concept of a device that takes heat As it flows from hot to cold, a process that does happen naturally and that creates entropy, and it diverts some of the energy, some of that thermal energy, and turns it to work. They're generically known as heat engines. And there are lots of heat engines in the world. The lava lamp, is it going to get going here? It's still warming up. The oldest of the human heat engines is this guy. I haven't used this for a couple of years. This is called Hero's engine. It's just a bottle with water in it. And I'm going to heat up the water until the water boils, which should happen pretty fast because it's not much water and it's a huge burner. And once the water boils, it will become steam, and then as the temperature goes higher, the pressure of the steam will go above atmospheric pressure, so it will accelerate towards atmosphere. And that acceleration will take it out some fine holes at the back, and as the gas is shot out those holes, it pushes back, and so it's like basically rocket, it's rocket propulsion, but this is rocket propulsion driven by boiling water. And one of the vanes is pointing in one direction, and the other is the opposite direction, so it's going to have a torque on it as it shoots the gas out. And it should start to spin. Ready? Now it's boiling now, and around it goes. Okay? So we're taking thermal energy. Whoa! It's survived. Woo! I always worry about these ones. Sometimes I can blow myself up. It does have a cork that will pop, but we took thermal energy and got work out of it. And not very useful work, but work nonetheless. And that will only work when you've got two different temperatures around. We have the boiling water, which is one temperature, and we have the cold room air, which is the other temperature. And off it goes. Let's see what other heat engine is going to get going. The lava lamp is slow. Another one is, I left the plan ahead. Holiday season, hey. So more thermal energy. I'm burning candles. All we got around there is thermal energy. Can you pivot? Okay. I'm turning it. I started it the wrong way. I'm not sure it's going to go. But the candle flames, because they're the hottest thing around, the gas in them is buoyant. It rises up by convection. Here it goes. Not very fast, though. Barely. A little disappointing. But as the air rises, it works on the blades of a fan, essentially a turbine, and causes it to spin very slowly. I think I can show this. Let's see. Preset 1. Yeah. So I'm barely getting the turbine to go. I can cheat, but what's the point? A little bit of action, not much. So it's using thermal energy, the temperature difference between the hot flames and the cold room air to get the most minimal amount of mechanical work done. I guess I'm 4 years old. Dippy Duck here is also a heat engine. It's a more obscure one. Dippy Duck keeps taking a drink of water and then tipping and going back. What's making it operate is not so directly a difference in temperature, although that's part of its action, but really it's a difference in order. It's consuming order. And you might think, what order is it consuming? It's consuming the order that's present in having a full container of water in the midst of air that's relatively dry. That is actually a somewhat orderly system. The more disorderly system is one in which the water has evaporated from that container and gone out into the room air to make it moister. In fact, the most disordered system that can possibly happen is 100% relative humidity. When the water and the air are in equilibrium, that is as disorderly actually as possible. You can also think of this as the disordering that comes with mixing. If you have blue socks and orange socks, nature likes to have those mix because that makes it disordered. If you have liquid water and dry air, nature likes to have that mix because that makes disorder. Is that okay? So what Dippy Duck is doing, in fact, is using the evaporation that comes with getting his head wet, or her head wet, and that cools her head while her behind is still at room temperature. And that temperature difference allows her to move a fluid, I don't know what the fluid is, up and down by pressure changes and evaporation changes. And so the fluid goes up towards her head, unbalances her, she tips over, the fluid pours back to where it started from, and at the same time she gets her head wet again. So it's using that difference in temperature between a wet head and a dry butt to do mechanical work. Not very important mechanical work, but fun anyway. Okay? So long and short of it is you can use the flow of heat from hot to cold to do things. You can divert it and make work out of it. So let me bring the camera back to normal and pull it off the screen. So that then leaves the automobile engine. So how does the automobile engine do it? Technically, it's taking the heat flowing from the very hot burn gas to the cool outdoors, and it's diverting some of it. It can't divert all of it. That would violate the law of entropy. And the fraction that it can convert depends on temperature. The bigger the temperature difference between the burn gas and the great outdoors, the larger the fraction of thermal energy it can divert and get action out. So people have asked over the years things like, on a cold day, can you get more, is your engine more efficient? And in principle, the answer is yes. In practice, I'm not sure whether they can take advantage of that, but that's the idea. The colder it is, the more efficient the gas engine becomes. Are the concepts between steam and combustion engines the same but with different materials? Absolutely. A steam engine is known as an external combustion engine because you burn the fuel outside the engine, making steam, and then the hot steam and the cold outside or the cold cooling pond or whatever, they divert some of that thermal energy and turn it into work. An internal combustion engine, the car engine, you burn the fuel inside the engine. That's what the word internal means. It's why it's distinct from a steam engine. But otherwise, they're very similar. And if you sort of start changing nouns and look at pistons and cylinders, you can make one into the other practically. All right, so will the duct thing go on forever? It will go on until it runs out of water or the room air becomes 100% humid, which again is the maximum entropy situation. At that point, it can't do anything anymore because if it runs out of water, that's just sort of a boring end of the story. But if it saturates the room air, evaporation stops. And Dippy Duck can't keep her head cold anymore because the water just sits there. And so there's no temperature difference between head and butt, and it stops. Okay, so things with order, systems that have order in them and nothing and no source of additional order will go through their motions until they've used all the order up, and they are as random as possible, and they have as much entropy as possible, and then they have to stop. There's nothing left to act. Okay, so an internal combustion engine, it does actually burn the fuel inside the engine. And let me walk you I will do this. Can I do it like this? No, I got to go this way. Okay. I'll walk you through the strokes of a conventional internal combustion engine, in part because you just should know how these things work. There is the problem that with the passage of time, these may become obsolete, but they're here now still. Electric systems are just a different story and not one for this semester, but most of the cars on the road still use this specific process to turn thermal energy into mechanical energy. They have pistons and cylinders that go through 4 strokes. So in fact, they have a collection of pistons and cylinders. A piston being the internal piece that moves in and out of a housing known as the cylinder. So it slides in and out of that cylinder. And the cylinder, we've sliced through it approximately. So you can see inside the cylinder. The cylinder is a can that's continuous all the way around. So it's like a soda can with one end cut off, and into that end is inserted the piston, which is a solid cylinder that fills that gap created by cutting the end off the can. At the second end of the can, the top end, are some valves and an electric spark plug in a conventional gasoline engine. So the idea is that the piston moves back and forth in this cylinder, and the gases that are involved are all trapped or move around inside the volume defined by the cylinder on the outside and closed at the top, and the piston moving in and out of it. Is that okay? It's basically the same concept. Actually, I should illustrate with as this thing. This is the cylinder, and this is the piston, in and out, okay? There are 4 strokes that happen, and they all matter. And I'll walk you through the 4 strokes. The first, and the names, who cares? The names are the names, but not important. The first is called the induction stroke, and the idea is that you want to fill the trapped volume inside the cylinder and piston with flammable stuff. So the piston as the piston pulls out of the cylinder, so not yet, now, as it pulls out of the cylinder and expands the volume inside, the trapped volume, the pressure drops in there, and gases can flow in, like air can flow in, and at the same time the air is flowing in, jets of gasoline under high pressure shoot in as well from what are called fuel injectors. So during the induction stroke, a valve opens at the top of the cylinder, letting air flow in as the piston comes out and shooting fuel in at the same time. So you've got gasoline and air mixing in this enlarging trapped space. Okay? That's the induction stroke. At the end of the induction stroke, the valves at the top of the engine cylinder close, so it's now sealed. So now you've got a container with flammable gas inside there, flammable mixture, and it's trapped, everything's closed, and the next stroke is the compression stroke, which basically shoves the piston into the cylinder and squishes that gas down tight. The act of squishing it down tight involves work. The piston is pushing the gas inward, and the gas is moving inward. That's work. So a lot of energy goes into the gas as it's being squeezed, and as a result, its temperature rises dramatically. We'll come back to that in a minute. Okay, so the compression stroke, it ends with the gas being highly compressed, the piston right up there at the top of the cylinder, the gas is under great pressure, it's very flammable stuff, it's ready to go. And then the spark plug fires, kaboom, and the gas burns, the whole gas. It was hot already, and now it is crazy hot, which is good because the higher the temperature you got, the bigger the temperature difference between that hot thing and the cold outdoors. So you can get more energy out of it. You can get more work out of it, a larger fraction. So the next stroke is the power stroke, where this very hot, very high pressure gas now does work on the piston as the piston moves out of the cylinder. And that's the power, the mechanical power that makes the cargo, is that expanding super hot gas doing work on the piston. And as the gas expands and does work on the piston, it's losing energy. The energy is going into the piston and making the car move. So the gas gets cooler. So by the time the piston is back to where it started, I've sealed this guy, so I can't go in and out without like suffering. So we did the induction stroke to suck the fuel and air mixture in. We did the compression stroke to pack it tight, spark plug fired. And now we do the power stroke as the gas shoves the piston out and does crazy work on it. And when the piston gets back to where it started, the gas has expanded a lot, its pressure has dropped a lot, its temperature has dropped a lot, but it's still got some pressure left. It's still way above atmospheric pressure. It's still considerably hotter than the great outdoors, and the original air. But you can't do a thing with it anymore. Or it's actually, you can do a little, but not much. And so you basically just open another valve and throw it away, the exhaust stroke. So they pop open a valve, let the gas leave as the piston goes in and squirts out the last of that burned gas. And that opening of the valve, while it's got a volume of trapped hot, high-pressure gas still inside it, makes a big pop sound. If it weren't muffled by a muffler, it would be pop, 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 pop every time they opened the valve at the end of the power stroke. And that's why some vehicles are very loud, because they don't have adequate mufflers, and some of them are very loud because the mufflers failed. But basically that pop, pop, pop that you're totally familiar for sure, of engines going by and stuff, that's the result of opening those valves at the end of the power stroke, when the gas just leaps out. What the muffler does is it smooths out the flow. So instead of being burst, 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 it's more whoosh, whoosh, whoosh. So they managed to make it less noisy. All right? Those are the four strokes that the engine goes through. A normal car engine has more than one cylinder for good reason. If all you have is one of these cylinders going through its process, 3 of the strokes are net losers for the engine. They take work. They don't provide it. It takes work to pull the piston out of the cylinder during the induction stroke to suck in air and fuel. It takes work to compress the fuel and air mixture to high pressure and high temperature and density. The power stroke provides work, good, and then the exhaust stroke, it takes work to squirt out the burned gas. So if all you have is a single cylinder going through the cycle, 3 of those strokes are a problem. One's good, one of them provides power. You can easily stall out, basically. The engine can stop during one of those energy expensive strokes. So normally you have an engine that has several of these piston cylinder assemblies going together, and they run out of sync. They're shifted in sync, so that one of them is always going through the power stroke and providing the work necessary for the other cylinders to do their jobs, to compress the gas, for example. So 4-cylinder engines, 6-cylinder engines, 8-cylinder engines, pretty common. In those cases, there's always one that's going through the power stroke, providing the work necessary to run the rest of the engine and to make the car go. All right? Couple of things worth having fun with. First one is what happens when you fire the spark plug to burn the gas. Is there really that much power, much energy around? And the answer is yes. And of course, have to show you. So instead of gasoline, I'm going to use methyl alcohol or methanol. And the first time I do this, I'll put it on gently. Second time I put it on hard. I'm going to fire it with a spark plug here. Ready? Get set. Oh, what's up? No electricity. Yeah. Okay. Ready? Oh, come on. That's boring. Okay, that's what happens. That's what happens if I put it on loosely. So yeah, one little poof. Okay, where's the air? There's air. Okay, out with the bad air, in with the good. Okay, now. So I'm trying to make it evaporate, of course, because the liquid doesn't burn. It's the gaseous methanol that burns. And the same thing actually is, it's involved in all these internal combustion engines. If they don't manage to get the liquid fuel into a vapor, it doesn't burn as well. And so you get smoke, and particularly diesel exhaust, the black stuff that you see shooting out of diesel engines. Diesel engines operate a little differently because they don't, how they do the ignition. But they basically just charcoalize the little droplets of diesel fuel, which then come out as soot, which is just nasty stuff, right? So gasifying the fuel. Now I'll shove it on tight. Ready? Expect a bang, I hope. Yeah. Yes. All right. Yeah. Actually, about the diesel engine. The diesel engine has no spark plug. And you might think, well, what the heck ignites the fuel-air mixture then? And the answer is the actual compression of that fuel and air, the compression process causes the fuel to burst into flames. And it happens in ordinary cars as well, but it's not desirable in ordinary cars. It's part of the diesel engine concept, which I'll say down in a minute. But in an ordinary car, that ignition during the compression stroke is a bad thing, is a problem. You know of it perhaps as knocking or pre-ignition. What's the idea? They mix fuel and air in the induction stroke. They then compress the bejeebers out of it, and its temperature skyrockets, and it can ignite without the spark plug. If that happens, your car knocks. It bursts into flames early, and I can show you that's possible. I'm going to put a little piece of cotton down here into a little container, and I'm going to compress the air like crazy. And when I do that, it's going to get so hot that piece of fluff will ignite. Not because of friction, but just because of the compressing the gas makes the temperature shoot up to hundreds or thousands of degrees. Ready? Get set. Okay? No friction, just compression. And so that problem limits the compression process in an ordinary automobile. You can't compress it as far as you'd like, perhaps, without it igniting spontaneously. So what do? Well, you back off of the compression, and you use a fuel that's hard to light. And that's the whole idea behind the grades of gasoline. When you go to the store and you shop for grades of gasoline, the only thing important you're buying, set aside all the hype, is how hard it is to light the fuel. Regulars, hard, but not super hard. The premium gasolines are harder to ignite. That's all you're buying. And most cars work fine on regular. It's already hard enough for them to ignite the fuel. The fuel is already hard enough to ignite that they do not cause this problem. So don't buy premium gasolines if your car is comfortable with normal. You're doing nothing except spending money. And what else? I mean, they'll pitch you all sorts of things. That's, the so-called 87 octane. It's good enough for most cars. And if your car doesn't knock, you're great. What is knocking like? You hear it as kind of like marbles rattling around in your engine. The ping, ping, sounds that happen because the ignition is occurring before the spark plug fired it, and it's not properly timed, and so the engine sort of jerks. And so you hear the jerky sound of that pre-ignition. And most cars don't do it. Sometimes when you're going up a steep hill, a normal car operating a regular will knock a little bit, but otherwise, the premium gasolines are for people with cars with high compression engines that go beyond what you're supposed to do with a normal car, and they get the knocking effect. Diesel engines, I'll finish by saying 2 cents about diesel engines. Diesel engines actually use that effect to do their ignition. They don't put the fuel in before the compression stroke. They compress the pure air to very high pressure and temperature and density. And it's so hot and high pressure dense that when they squirt oil into it, diesel oil into it, the diesel oil bursts into flames. And so the diesel idea is compress the bejeebers out of pure air. You can do that. It's not going to burst into flames. and then shoot in the gasoline. They do it at like 30,000 PSI. They just shoot a little jet in there. And it bursts into flames, and then everything else is very similar. The diesel engine wants a fuel that ignites easily. A car engine wants a fuel that's hard to ignite. This is why you don't mix the two. You don't go from one to the other. Don't put diesel in one, an ordinary gasoline engine and vice versa. All right, so that's the story of automobiles, and we'll go on to other things on Friday.